Greetings, differential equation scholars, and welcome to this next video in our series on the Laplace transform. In our previous videos, we've taken a look at using the definition to discover what the Laplace transforms of constants and exponentials and polynomials are. And we've even taken a look at the Laplace transform for a piecewise defined function. Well, one other important class of functions that we'd like to understand the Laplace transforms for are trigonometric functions like the sine and the cosine. One important result that is quoted in section 7.1 is that the Laplace transform of the cosine of k times t is s divided by s squared plus k squared. So that, for example, the Laplace transform for the cosine of 6t is equal to s over s squared plus 36, with k equal to 6 in this particular case. That's a very useful rule, but where does that rule come from? And where does the analogous rule for the Laplace transform for a sine come from? In this video, we'd like to take a look at the derivation for this rule that the Laplace transform of kt, the Laplace transform of the cosine of kt, is s divided by s squared plus k squared. So let's take a look at the origin of that rule. Of course, we've got to go back to the definition. The Laplace transform of any function, such as the cosine of kt, is the improper integral from 0 to infinity of e to the minus st times that function. So here, as an integrand, we have the product of e to the minus st and the cosine of kt. And we need to find that antiderivative and then evaluate it in the limit, as the upper limit is going towards infinity. Well, let's concentrate on what the antiderivative is first. You probably remember from previous calculus in your discussion of techniques of integration that when we have a product of an exponential and a cosine or a sine, one approach that we can use is repeated integration by parts. So we're going to do 2 rounds of integration by parts to resolve this antiderivative. In the first stage, we'll let u be e to the minus st, and we'll let our dv be cosine of kt dt. With those allowances, then the derivative of u, du, is negative s times e to the st dt, and v, which is our antiderivative of dv, will be 1 over k times the sine of kt. Now, when we take those results and we use them with integration by parts, we always find that the antiderivative of u times dv is u times v minus the integral of v times du. Now here, as we're taking the negative of the integral of v du, bear in mind that v du has a net negative sign when we multiply v and du together. So as we're subtracting the integral of v du, that's really like adding an integral here, since we're subtracting a negative. And note the factors of s and 1 over k here that don't depend on t. So here we've pulled those out front here as plus s over k. And what's left over in the integral of v du is a negative exponential times a sine. So now, after having broken down this integral of e to the minus st times the cosine, we have obtained an integral that involves e to the minus st times the sine. Well, using integration by parts, we could approach that integral in a similar fashion. Once again, we'll let the exponential be our u, so that du is negative s e to the minus st dt. But now here we're going to let the dv be the sine of kt dt, so that its antiderivative is negative 1 over k times the cosine of kt. So with those choices of u and dv and the resulting du and v, integration by parts would tell us that antiderivative of u dv is u times v minus the integral of v du. And you can see our v and our du, their product here is a net positive. So we really do have a subtraction here. And once again, we have factors of s divided by k that can be pulled out in the front. So now, combining these two results, our first result gave us one piece plus an integral. And now that integral itself has two pieces, the second of which is an integral. When I replace the antiderivative of the e to the minus st sine of kt with this sum, here's what we're going to find. We're going to find that our original antiderivative here of the negative exponential times the cosine is 1 over k times the negative exponential times a sine term plus, and then we're going to have effectively negative s over k squared times the negative exponential times the cosine minus s squared over k squared because of the distribution here times, and note this, the very same integral that we started with on the left-hand side. So that expression for the Laplace transform of the cosine of kt now appears on both sides of the equation. And that suggests an algebraic route to solving for it. Because if the thing that we're solving for appears on the left and on the right, what we could do is we could add this expression from the right-hand side to the left-hand side of the equation. And that'll give us that 1 plus s squared over k squared times the integral that we're trying to solve for equals the sum of the first two terms appearing on the right-hand side. Aha! So now this tells us that if we just evaluate these two expressions on the right-hand side and then divide by the expression that would be k squared plus s squared over k squared, we will have the result that we want. We will be able to solve for the Laplace transform of the cosine of kt. Well, what do we get when we evaluate these functions on the right-hand side? Well, there's two parts to that. The first part is a limiting piece where we substitute in b to these two expressions and let b go to infinity. And the second part is subtracting off what we get when we evaluate these at 0. Well, let's talk about each of those parts. The first part, the limiting part. When we substitute in b for t and let b go to infinity, take a look at these terms that we have here. This first one here is a negative exponential times a sine. And the second piece is a negative exponential times a cosine. What happens to those in the limits as the argument for the negative exponential is decreasing without bound? Well, the cosine and the sine functions are bounded. They always have a value that stays between -1 and 1. And because they are bounded, and because the exponential term is going to 0, that means that both of those terms in the limit are going to go to 0. That means the only thing that'll be left will be what we get when we evaluate the functions at 0. But at 0, the first piece involving a sine has a value of 0. The second piece ends up having a value of negative s over k squared times 1 times 1. But ultimately that's being subtracted because it's at the lower limit. And so what we end up with in the final result is that what we get when we evaluate this is just s over k squared on the right-hand side. Now we're looking to solve for the Laplace transform, So we multiply both sides by the reciprocal of k squared plus s squared over k squared. And then when we do that evaluation, k squared divided by k squared cancels out, and we get the result that we were looking for, s divided by k squared plus s squared. And that's the Laplace transform for the cosine of kt. And we found that again by using integration by parts twice in a row, and then using an algebraic technique to solve for the value of the integral. A very nifty result, and perhaps you remember doing problems similar to that when you studied integration by parts. Now, you can use that exact same approach to derive the rule for the sine of kt, and it turns out you get a result that is similar, but with one key difference. Notice that in our rule for the Laplace transform for the sine of kt, that the denominator is exactly the same as it was for the cosine, s squared plus k squared. But the key difference, when you do the Laplace transform for a sine, instead of having the variable s in the numerator, which we get with the cosine, we get instead the value of the constant multiplier k. So the denominators are the same, s squared plus k squared, but the numerators are different. Let's take a look at an application of using both of those rules together. Suppose somebody asked us to find the Laplace transform of the cosine of 3t plus twice the sine of 3t. Well, when we want to find that Laplace transform of the sum, we can use our knowledge that the Laplace transform is a linear transformation. And all we need to do is to find the Laplace transform for the cosine of 3t and add to that twice the Laplace transform of the sine of 3t using our rules of linearity. But now we know how to find those, because in both of these, k is equal to 3. S squared plus k squared is s squared plus 9. So the Laplace transform for the cosine of 3t will be s divided by s squared plus 9, the k squared on the bottom there. And the Laplace transform for the sine of 3t will be k over s squared plus k squared. So 3 over s squared plus 9 for the Laplace transform of the sine. Now we have twice that transform, so 2 times 3 is 6. And since both of these happen to have the exact same denominator, it makes sense that we might just simplify our result by writing it with a common denominator. When we do that, we'll see that we have s plus 6 divided by s squared plus 9. So the Laplace transform of that linear combination of cosine of 3t and the sine of 3t is s plus 6 divided by s squared plus 9. And that's an example of applying both of the rules for the Laplace transform of the cosine and the Laplace transform for the sine. These two rules will be two additional valuable tools to add to our arsenal as we're solving differential equations eventually with the help of Laplace transforms. So please take some time to practice with those rules, for we will find them to be indeed very useful to us going forward.